Derivative formulas. In the previous section, we looked at how we could define a derivative by using limits. We were able to find various functions and their derivatives by using the limit as h goes to 0 of f of x plus h minus f of x over h. Let's look at this for a couple more examples, and then we'll recap the ones we've already looked at. So let's suppose we want to find the derivative of a constant, f of x equals c. So remember, if your function is a constant, that means you have something like y equals 5 or y equals -2. If it's constant, it's just a straight line that's horizontal. So we're trying to find the derivative of this function. So again, we're going to apply our formula, which we see down here. If you plug in an x plus h into f of x equals c, you just get c because there is no x to plug into. Similarly, f of x also equals c. So we end up with the limit as h goes to 0 of c minus c divided by h. Well, since c minus c equals 0 and h doesn't ever equal 0, it just gets really close, 0 divided by anything is always 0. So we find that if our function is just a constant by itself with no variable in it, then the derivative is 0. And this makes sense because remember, the derivative is the slope of the tangent line. A tangent line to a linear function like we have here is going to lie on the line, which means it's going to have the same slope as the function itself. And you can see here that whenever we have a constant, it's a horizontal line. And we know that the slope of a horizontal line is always 0 for every point. Therefore, it makes sense that if we were to find the derivative of a constant, it would be 0 everywhere. Let's look at another. Suppose we want to find the derivative of a linear function. So remember, a linear function is a line that has some sort of slope m. Now, here, like before, our tangent lines will lie on the line, which means every single tangent line is going to have the same slope as the line itself. Therefore, the slope of every single tangent line is going to be m. But let's show this a little more carefully. So again, starting with our definition of derivative, if we plug in an x plus h into mx, we get m times x plus h minus f of x, which is mx, divided by h. If we distribute the m, we have mx plus mh minus mx. So we have an mx and a minus mx, so those will cancel. And we're left with mx over h. So here, the h's will cancel. And we end up with the limit as h goes to 0 of m. Since there's no h's left, that just equals m. So what that tells me is that if I have a function that's m times x, that the derivative is just that m. And remember, m is just a constant. It's the number that represents the slope of the line. So now we have two new statements from our definition to add to the two that we'd previously looked at. So let's remember the two that we'd already calculated. So earlier in the term, we used the definition of derivative to find f of x equals x squared has a derivative of 2x, which we can also write as 2x to the 1. Additionally, we use the definition of derivative to find that the derivative of x cubed was 3x squared. So when we add those to the two that we just talked about, the derivative of a constant and the derivative of mx, there's a pattern that begins to form for polynomials and power functions. So again, these are functions where x is raised to a power. If we do enough of these, we see that the derivative of a function x to the p has the form px to the p minus 1. So what that means is when I have a function like x cubed, the 3 comes down in front, the power comes down in front, and then we subtract 1 from the power. When we have patterns, that's how we get formulas. So in this section, we're able to find and use various formulas for derivatives so that we no longer have to calculate them by approximating really close to the point. We'll now have a way to find the formulas exactly so that we will no longer have an approximation, but an exact answer. So let's look at a table of all the formulas we know so far from the patterns that we've discovered. So far, our derivative formula list is comprised of 3 functions. So here we have a constant, the derivative is 0. If we have a constant times x, the derivative is just that constant. And if we have x raised to some power that we're calling p, then the derivative is px to the p minus 1. So we're going to be adding to this formula list for the rest of this chapter, but we're going to start with these 3 formulas and we're going to practice finding derivatives using these formulas. Remember, c, m, and p all represent constants here, and x is our variable. Example 1. Use the formulas to find each of the following derivatives. So for part A, I have f of x equals 7. That's a constant. That means that if I were to take the derivative of that, I would get 0, because the derivative of any constant that's by itself is just 0. For B, I have 10x. So that's in the form mx. I have a number times x, which means when I take the derivative, it's just that number. Notice that a and b are different. A is a constant that's by itself, whereas b is a constant attached to the variable. So these result in different outcomes. Part C, I have x squared. So the rule for polynomials and power functions is that the 2 will come down and I will subtract 1 from the power. So I get 2x to the 1. Part D, I'm going to use the same rule, only now I have a power of 5. So the 5 comes down and I subtract 1 from the power, 5x to the 4th. For part E, I have to be extra careful here because my power is negative. So I get negative 4x to the negative 5. So if you have a negative 4 and you subtract 1 from the power, you get more negative. So you get negative 5. If we have x to the 2/3, that means the 2/3 will come down in front. And then again, we're going to subtract 1 from the power. 2/3 minus 1 gives me negative 1/3. So again, be careful with fractions. And then finally, our last example here, G, we have x to the negative 4/5. So the negative 4/5 comes down in front, and then we subtract 1 from the power. Negative 4/5 minus 1 is negative 9/5. So here, applying the rules that we have so far, we're able to take the derivative of all sorts of functions where our variable is in the base and we have a numeric power. Now your variable doesn't have to be x. We could have used f of t or c of q. If we change the variable, the rule doesn't change. But here, we're using x just to get us started and used to these formulas. Derivative with a constant multiple. So if you have a constant times your function, and you're trying to take the derivative of that, then you can pull the constant out and multiply the constant times the derivative of the function. So what does that look like? Let's look at an example real quick. So suppose we have the function f of x equals 2x to the 7th. So here, the 2 is the constant, and the x to the 7th is going to be our function, which means that when we take the derivative, it's going to be 2 times the derivative of x to the 7th. So our rule says that the 7 will come down in front, and we'll subtract 1 from the power. So the derivative of x to the 7th is 7x to the 6th, but the 2 multiplies that. So I can multiply the 2 and the 7 together, and I get 14x to the 6th. Now usually we don't write out this in-between step. Instead, what we do is when the 7 comes down, it just multiplies whatever is in front. and then we subtract 1 from the power. But when you have that constant in front, it's not by itself. So the derivative of that 2 is not 0 because it's attached to the function. So let's try a couple of examples with constants in them so we can practice using both our rules and this new rule about the constant multiple. Example 2. Use the formulas to find each of the following derivatives. So the first one, we have f of x equals pi. Now remember that pi is a number. Okay, pi is a constant. It's approximately 3.14159. And so when we take the derivative of a constant, we said that the derivative is 0. So don't let the fact that it's symbolic fool you. It's still just a number. Another example of this is e. When e is by itself and not e to the x, then e is also just a number. So for the next one, we're going to use our constant multiple rule paired with our power rule. So here the 3 is going to come down and multiply the 4, giving me 12x, and now we subtract 1 from the power, so 12x squared. For the next one, we have 9x to the 20th. So the 20 is going to come down and multiply the 9, giving me 180x. Now we subtract 1 from the power, and we get 19. For the next one, notice that we have a negative 3 in front. So when the 5 comes down, we get negative 15x, and then we subtract 1 from the power to the 4th. For the next term, the negative 6 will come down and multiply the 6, giving me negative 36x to the negative 7. For f, here we have 1/3. So the 1/3 is going to come down and multiply the 6. When you multiply 6 times 1/3, you get 2x. Now 1/3 minus 1 is negative 2/3. So we get 2x to the negative 2/3. And then finally, for part G here, this negative 2/5 is going to come down and multiply the 7. So I get negative 14/5 x to the negative 7/5. So again, we're using our rules to find derivatives, but let's remember what this is telling us. What this is doing for us is it's giving us a function, that is the derivative function, where we can plug in any number we want to get the slope of the tangent line to the original function at that point. So for example, if I go back to part B, if I were to find f prime of 1, and I were to plug a 1 into the derivative, I would get 12 times 1 squared, which is 12. What that tells me is that 4x cubed, the original function, is changing at a rate of 12 units in the dependent direction for every 1 unit in the independent direction when x equals 1. So if I were to draw 4x cubed and I were to go to the point 1, 4, where that point is, and draw in the tangent line, the slope of that tangent line would be 12. So this function, 12x squared, allows me to find the rate of change at any point for 4x cubed. Let's keep going. So when we do some of these, occasionally there's algebraic rewrites that have to be done before we can even use the power rule, because we can only use the power rule if it's in the form x to the p. So x has to be raised to some number. So let's look at a few examples where we have to do some rewrites first. Example 3. Use the formulas to find each of the following derivatives. So the first one is the square root of x. The square root is a symbol that actually represents a mathematical property, which is the power of 1/2. So the first thing we need to do here is we need to rewrite this function as x to the 1/2 power. By turning that square root back into a number, that's going to allow us to use our power rule to find the derivative. So now we can go ahead and the 1/2 will come down and we subtract 1 from the power. So we get 1/2 x to the negative 1/2. Now, we'll come back to that in a minute in terms of simplification, and we'll talk a little bit about in part B. But let's go to part B first. So for part B, we have 4 over x cubed. We cannot take the derivative of x cubed just in the denominator. So that means we have to get it out of the denominator to be able to even start to take the derivative. So algebraically, we can rewrite this as 4x to the negative 3. You can bring a term out of the denominator if you change the sign of the power. So that means we can bring it up as long as we make that power of x negative 3. So that means when we take the derivative of this function, the negative 3 will come down to multiply the 4, giving me negative 12x, and now I subtract 1 from the power, so to the negative 4th power. Now, I can use the same algebraic trick here to put this term back in the denominator. So I could simplify this as negative 12 over x to the positive 4. So again, I'm able to put it back down by changing the power to be positive. If we go back to part A, if we wanted to simplify this one, we would put that term in the bottom, but notice that we have a 1/2, which means we already have a 2 in the bottom. So I could write it as 1 over 2x to the positive half, and I could even take it a step further and put the square root back in. So 1 over 2 square roots of x. These are all algebraically equivalent. In mathematics, generally we don't like to leave powers as negative, so we do often put the term back down into the denominator. Let's look at C. So for C, we have the 5th root of x squared. So again, we can't do much here without doing some algebra first. So the first thing we want to do is we want to get rid of this symbol, the root symbol. The 5th root is the same thing as something raised to the 1/5 power. Whatever that number is inside the root, you're going to raise it to 1 over that power. If there's no number there, then it's a square root, and you raise it to the 1/2. Now, with exponential functions, if you have a power raised to a power, you can actually multiply those powers together. So 2 times 1/5 is x to the 2/5. Hopefully you remember that from algebra. Now that we have it in this form, x to the 2/5, it's in perfect form for us to use our power rule. So now we take the derivative, the 2/5 will come down in front, and we subtract 1 from the power, so 2/5 minus 1 is going to give me negative 3/5. So we can either leave it like that, or by practicing our algebraic simplification, we can write this as 2 over 5x to the positive 3/5. So we'd probably leave it like that. If you wanted to make it even more simplified, you could take it a step further, and you could say 2 over 5 times the 5th root of x cubed. Now, if you're putting answers in on Wiley, any of these should be accepted. So I would caution you from oversimplifying unless you're really, really, really solid in your algebra. All right. So now let's look at another rule that we can apply to derivatives. Derivatives of sums and differences. So if you have two functions added together, f of x plus g of x, and you want to take the derivative of that, turns out you can take the derivative of f of x plus the derivative of g of x. Similarly, if you have two functions that are subtracted from one another, you again can take the derivative of each function individually and subtract their differences. So what that means is if you have a function of things that are added and subtracted, you can go term by term using the rules to take the derivative, and you will get your resulting derivative by adding or subtracting them in the same order that the original function was presented. So let's go ahead and try a couple of examples that use this property. Example 4. Use the formulas to find each of the following derivatives. So notice here that we have multiple terms in one function. So here for part A, the sum and difference rule says that I can go term by term and take the derivative of each part. So I start with my x to the 5th. the derivative of that is going to be 5x to the fourth. The power comes down and you subtract 1 from the power. Minus, now we have 2x squared. So the 2 comes down to multiply the 2 from our constant multiple rule, and we get 4x to the 1 plus, now the derivative of 6x, when you have a constant times x, the derivative is just that constant. And then the derivative of 1 is 0. So that means that we're going to have 5x to the fourth minus 4x plus 6. We don't usually write the plus 0, and we also don't usually write the 1 power, but I'm writing it here now so we can see how the rules have been enacted. So now for part B, we have the function 3x cubed minus x to the 1/3 plus the square root of x. But again, that square root of x we can't work with until we rewrite it. So the first step is just to rewrite that last part of the function, which gives us f of x equals 3x cubed minus x to the 1/3 plus x to the 1/2. So this rewrite is going to be what allows us to take the derivative here. So again, now that we have that, we can go term by term. So the derivative of 3x cubed, the 3 comes down to multiply the 3. We get 9x squared minus 1/3 x to the negative 2/3, because again, 1/3 minus 1 is negative 2/3, plus 1/2 x to the negative 1/2. So the 1/2 comes down, and half minus 1 gives me negative 1/2. For now, you don't really need to worry too much about simplifying. You only need to simplify if you're asked to simplify, or if you need to use your derivative to find something further. So for now, just keep practicing the rules and don't worry so much about algebraic simplification of your answer. Part C. We have 10x to the fourth minus the fourth root of x plus 2 over x cubed. So again, this function demands a rewrite before we can actually use our power rule. So the first term stays the same, 10x to the fourth. But the second term, the fourth root of x, is going to be rewritten as x to the 1/4. Our third term, 2 over x cubed, we're going to bring that x cubed term up by making the power negative. So now that we've rewritten everything, we have things in the right form, which is x to some number. So now we again can go term by term and take the derivative. So the first term, the 4 comes down to multiply the 10, giving me 40x cubed, minus the 1/4 comes down, 1/4 minus 1 is negative 3/4. Now here, the negative 3 is going to come down to multiply the 2. So I'm going to write this as minus 6x to the negative 4. And again, it's minus because this negative 3 multiplied the 2, which would give me plus negative 6. So instead, I'm going to write it as minus 6x to the negative 4. Part D. Again, we're going to start with a rewrite because the last term has the square root of x in it. So I'm going to rewrite the last term as 2x to the 1/2 power. But now that I've rewritten it, I can go ahead and take the derivative term by term. So the first term, we had minus 3x to the negative 3/4. So here, the negative 3/4 is going to multiply the negative 3. So the negatives are going to cancel, leaving me with 9/4 x. Now negative 3/4 minus 1 is negative 7/4. The second term here, the 1/2 is going to come down and multiply the 2. Since half times 2 is 1, I can write this as 1 times x to the negative 1/2. You don't have to write that 1 in front of the x if you don't want to. Anything times 1 is just itself. But if it helps you remember the process of what you did in use of the formula, you're free to use it if you'd like. So now we've computed a bunch of derivatives that have multiple terms that are added and subtracted. The next rule that we're going to talk about has to do with second derivatives. The second derivative. So recall that the second derivative is the derivative of the first derivative, which we write as f double prime of x, or d squared y over dx squared if we're using Leibniz notation. Turns out that the formulas can be used the same way to find the second derivative as we used to find the first derivative, which means that if we have the first derivative of a function, we can apply the formulas again to find the second derivative. So the power rule will work on a first derivative as well. It also works for all subsequent derivatives, third derivatives, fourth derivatives, fifth derivatives, if you ever needed to find those. So let's practice computing first and second derivatives together. Example 5. For each of the following functions, compute the first and second derivative. So we're going to start with the function 6 minus 3 over x plus 3 over x squared plus x to the 1/3. So again, we have to start with a rewrite because we can't really do anything when our variable is down in the denominator. So we rewrite this as 6 minus 3x to the negative 1. So here, remember that there's an invisible little 1 here that we don't usually write. So if we want to bring that up, we have to make that 1 negative. Similarly, 3 over x squared becomes 3x to the negative 2. And then our x to the 1/3 stays the same. So now we can use that to find the first derivative. So again, we're going to go term by term. The derivative of 6 is going to be 0 because it's a constant. For the next term, the negative 1 is going to come down to multiply the minus 3, giving me positive 3x to the negative 2. Now for the next term, instead of plus, I noticed that my power was negative, and so when it multiplies that, I'm going to end up with minus 6x to the negative 3 plus 1/3 x to the negative 2/3. So that was my power rule that I'm using to find the first derivative. If I want to find the second derivative of this function, I'm going to take the derivative of the first derivative. So again, I'm going to go term by term. So the negative 2 will come down to multiply the 3, giving me negative 6x to the negative 3, because again, I'm subtracting 1 from the power. The negative 3 is going to come down and it's going to multiply the negative 6. So I'm going to get plus 18x now to the negative 4 because I subtracted 1 from the power. And then here, I'm going to have a minus 2/3 times a positive 1/3. So that's going to give me minus 2/9 x. So 2/3 times 1/3 gives me the 2/9. You multiply the numerators and the denominators. And then negative 2/3 minus 1 is going to give me negative 5/3. So we use the same process on the first derivative to get the second derivative. Let's try it for the other examples. Part B looks a little funny. So for B, we have x to the e. Now remember that e by itself is a number, like pi. So when we have x to the e, it's still x raised to a number. So we can still use our power rule here. So when we find the first derivative, our formula says that the number in the power is going to come down and we're going to subtract 1 from the power. So we can write this as e times x to the e minus 1. It looks a little goofy, but it still works and it still follows all our rules. To find the second derivative, we're going to take the derivative of the first derivative, which means that this e minus 1 is going to come down in front. So we have e times e minus 1. And now if we subtract another 1 from the power, we get x to the e minus 2. Now this one, like I said, it looks a little goofy, but if you can follow along and apply the rules when you know it's a number, you'll be in good shape for this type of problem. Part C. So we have 6x to the 7th minus 20 square roots of x. Again, we want to get rid of that square root so that we can actually have a number to work with. So we rewrite the last term as 20x to the 1/2 power. So now, when we want to find our first derivative, we're going to go term by term. So the derivative of 6x to the 7th is going to give me 42. 7 times 6 is 42. X to the 6th. And then our second term here, we have half times 20. Half of 20 is 10. X to the negative half. So that's our first derivative. Our second derivative, we're going to take the derivative of the first derivative. So the 6 is going to come down and multiply the 42, and that's going to give me 252 x, and now we're going to subtract 1 from the power, so to the 5th. And then our second term, we have a negative half that's going to multiply a negative 10. So that's going to give me plus 5x. Now negative half minus 1 is negative 3/2. So we get 252x to the 5th plus 5x to the negative 3/2 as our second derivative. Example 6. Consider the function f of x equals 1/3 x cubed minus 2x squared plus 3x plus 1. There's a lot of things we want to do with this function, and what's really important here is that we need to remember, even though we have these formulas to compute derivatives, we are still able to discuss all the same properties of approximation in terms of the relationship between the original function and the first derivative, things like increasing, decreasing. All of those relationships still exist, even though we now have a better way of computing the derivative. So let's see how this all works out when we relate what we were doing before to what we know now. So first, let's compute the first derivative. So again, the 3 will come down to multiply the 1/3. That's going to give you 1x, and we subtract 1 from the power to give me x squared minus 2 times 2 is 4x to the 1, plus the derivative of 3x is just 3, and the derivative of 1 is going to be 0 because 1 is a constant. So that means that my first derivative is x squared minus 4x plus 3. We want to find the values for which the first derivative equals 0. So remember, your first derivative is going to equal 0 when the original function is constant. That's where we have those horizontal tangent lines. So if we set our function equal to 0, we're going to want to factor this to find the roots. So we'll get x minus 3 times x minus 1 equals 0. So that means we're going to have the roots x equals 3 and x equals 1. So these are the two values that's going to be when the first derivative equals 0. So we want to know, when is the original function increasing and when is it decreasing? We said it's going to be increasing if the first derivative is positive, and it's going to be decreasing if the first derivative is negative. So if we were to draw a number line here, and we were to put on the values where it's 0, where this first derivative is 0, we will be able to tell what the original function is doing by figuring out the sign of the first derivative on these intervals. So if we want to know what's happening to the left of 1, we need to pick a number a little to the left of 1, say 0, and plug it in to the first derivative to see if we get something positive or negative. If we plug a 0 into the first derivative, we get 0 minus 0 plus 3. So we get something positive. If we pick a number between 1 and 3, say 2, and we plug it into the first derivative, 2 squared is 4, minus 4 times 2. 4 times 2 is 8, so 4 minus 8 is negative 4, plus 3 is going to give me negative 1. So between 1 and 3, my first derivative is negative. And then finally, something bigger than 3, so we can pick something like 4. So 4 squared is 16, minus 4 times 4, another 16 gives me 0, plus 3 is something positive. So this gives me the intervals where my first derivative is positive and negative, which tells me where my original function is increasing and decreasing. So I'm going to be increasing wherever my first derivative is positive, which was negative infinity all the way until 1. And again, from 3 to positive infinity. And then my original function is going to be decreasing where my first derivative was negative, which was between 1 and 3. So those relationships still exist. Let's keep going. Compute the second derivative. So when computing the second derivative, we want to go back to the unfactored form of the first derivative and use our power rule again. So the derivative here, the first term is x squared, so the derivative of that is going to be 2x to the 1. The derivative of minus 4x is minus 4, and the derivative of 3 is 0 because 3 is a constant. So the second derivative here is 2x minus 4. Part E, find the values of x for which the second derivative equals 0. So if we take our second derivative and we set it equal to 0, this is a linear function, so we don't need to factor it. We can bring the 4 over. We get 2x equals 4. So we find that x equals 2. So x equals 2 is what's going to make the second derivative equal to 0. Part F says, for which values of x is f of x concave up and concave down? So again, what we can do is we can look at what's happening around 2, because we know at 2, the second derivative is 0. So we likely are changing whether it's positive or negative. So we want to test something a little to the left of 2, say 1. If we plug a 1 into the second derivative, that's negative. We also want to test something a little to the right. If we plug a 3 into the second derivative, that's going to give you positive 2. So that means that to the left of 2, our second derivative is negative. If your second derivative is negative, that tells you that the original function is concave down. To the right of 2, our second derivative is positive. If your second derivative is positive, that tells you that the original function is concave up. So we're going to say f of x is concave up, right, when we're positive. So from 2 to infinity. And we're going to be concave down whenever the second derivative is negative, which is negative infinity until 2. Now, again, we said that at the point where the second derivative equals 0, we are likely going to have what's called an inflection point. So that's the point where we change concavity. So we're changing from concave down to concave up, because we start off concave down on the left side of the graph and we're concave up on the right side. So again, we can use our formulas in conjunction with all the things we knew before to talk about these types of things. Example 7. Students are pulling a 2 kilogram friction block along a rough but level surface. In one case, it's determined that the position of the block as a function of time can be modeled by s of t equals 0.3 t cubed minus 0.1 t squared plus 0.2 t. Part A. Find a function for the speed, which is the velocity, at which the block is moving on average during the first 3 seconds. When we talk about a block moving on average, that means we're looking for the average rate of change, and for the first 3 seconds means we're looking between 0 and 3. So we're going to do s of 3 minus s of 0 divided by 3 minus 0. So if we take 3 and we plug it into the above function, we're going to get 7.8 minus, and if we plug in 0, we get 0, all divided by 3. So when we plug that into the calculator, we're going to get 2.6. Now remember that s of t, right, is going to give us the position, and time is going to give us seconds. So our formulas didn't help us when we still had to calculate the average rate of change. However, in part B, when we're looking for the velocity at time equals 2, we're looking for an instantaneous rate of change. So here we can apply our formulas, because now we can talk about the velocity, which is the derivative of position. So here we're going to take the derivative of position, and we're going to get, so the 3 is going to come down and multiply the 0.3. So we get 0.9 t squared minus, now 2 comes down to multiply the 0.1, so 0.2 t to the 1 plus The derivative of 0.2t is 0.2. So we have a formula now for the derivative. We didn't have to approximate it really, really close to 2 by using things like 1.99, 2.01. Instead, we get the derivative function, and then we can calculate the velocity by just plugging in a 2 into the derivative function. So when we plug in 2, we'll crunch those numbers, and we're going to get 3.4. So we were able to find an exact velocity rather than an approximated one because we now have a formula that lets us do polynomial derivatives. Part C, find a function for acceleration as a function of time. So as a reminder, acceleration is the derivative of velocity, or what's called the second derivative of position. So here, if we take the next derivative, which is the derivative of velocity, we can find the function for acceleration. So the 2 will come down and multiply the 0.9, giving me 1.8t. Now here we have minus 0.2t, so the derivative is minus 0.2, and then the derivative of the 0.2 that's by itself is just 0 because that's a constant. So now we have a function for the acceleration. Having this is very powerful because we could compute the derivative or the velocity at any time, as well as the acceleration at any time, because now we have a way to find those formulas. Example 8. Find the equation of the tangent line to f of x equals x squared minus 4x plus 1 at x equals 3. So let's remember what our derivative tells us. The derivative is going to give us the slope of the tangent line at a point. So that's part of what we need to find the equation of the tangent line. The other thing that you need to get the equation of a line, if you have a slope, is a point that's on that line. Well, the point at x equals 3 is the one point that's shared by both the tangent line and the function. So in order to figure out this problem, we need two things to put together the equation of the tangent line. We need f of 3 and we need f prime of 3. F of 3 is going to give us the point that's shared between the tangent line and the function. So f of 3 means I'm going to take 3 and I'm going to plug it into my given function. So 3 squared minus 4 times 3 plus 1. So that's 9 minus 12 plus 1, which is going to give me negative 2. So that means f of 3 equals negative 2, or we can write the coordinate point here, 3 comma negative 2. That's the point where the tangent line touches. Now if we find the derivative, we'll be able to find the slope of the tangent line at 3. So over here, we'll find the derivative of our function using our rules here. So the 2 comes down and we subtract 1 from the power, minus the derivative of 4x is 4, and the derivative of 1 is 0 because 1 is a constant. So f prime of 3 means that I'm plugging a 3 into my function here. So I have 2 times 3 minus 4. So 2 times 3 is 6. 6 minus 4 is going to give me 2. So remember, that's the slope of the tangent line, right? The derivative tells us the slope of the tangent line. So now I need to take my point, 3 comma negative 2, and my slope, 2, and put that together to find the equation of the line. So the equation of a line can be written as y equals mx plus b, or y minus y1 equals m times x minus x1. Either is fine, but I'm going to use the y equals mx plus b form to figure out this problem because that's the way I generally do it. If you want to use the other form, that's fine as well. So here, my slope is 2, so I have y equals 2x plus b. Now to find my b, that's why I need my point, because I need to plug in the point to be able to solve for b. So I'm plugging in a 3 for x and a negative 2 for y. So that leaves me with just a b, and everything else is a number. So 2 times 3 is 6. So I'm going to subtract 6 from both sides. And that's going to tell me that b equals -8. So once I know what b is, I can put everything together to get the final equation of my line. My slope was 2, so I have y equals 2x minus 8. So that's the equation of my tangent line at this point. So this again is at the point 3, -2, and the equation of the tangent line is 2x minus 8. Now that we have good practice on our power rule, we can add 2 more derivatives to our formula list. The first is that of sine. The derivative of sine is going to be cosine. If we were to approximate the derivative at every point and plot those derivatives, so graph the derivative like we had in a previous section, we would see that the derivative of sine follows all the properties of cosine. Similarly, we also have the derivative of cosine. The derivative of cosine is going to be negative sine. So we can add those to our formula list so that now we'll have 5. So let's do some practice problems now that we know the derivative of sine and cosine that include those. Example 9. For each of the following functions, compute the first and second derivatives. So let's start with 6 times cosine. So the constant multiple rule works for all derivatives we're going to be looking at. If you have a constant times a function, the derivative will always be that constant times the derivative of the function. So here, we said the derivative of cosine was negative sine. So we have 6 times negative sine, which is -6 sine x. The second derivative is going to be the derivative of -6 sine x. So that means we're going to have -6 times the derivative of sine. The derivative of sine is cosine. So again, the first derivative here is -6 sine x, and the second derivative is -6 cosine x. If we were to keep going, we would get another sine, another cosine, and then another sine, another cosine, because these are cyclical, and what would change is whether or not we had a positive or negative in front. Part B, sine x plus 1. So we said that the derivative of sine is cosine. So we start with that term. So we get cosine x. Now the derivative of 1 is 0 because it's a constant. So now the second derivative means we're taking the derivative of cosine, which from our chart is negative sine. So our first derivative is cosine of x, and our second derivative is negative sine x. Part C. We have x cubed minus 2 sine x. So our first derivative, we go term by term. We get 3x squared minus 2. Now derivative of sine is cosine. So minus 2 cosine x. And our second derivative, the derivative of 3x squared is 6x. And now the derivative of cosine is going to be negative sine. So the negative from the negative sign will cancel the negative in front of the 2. And we get plus 2 sine x. So the second derivative is 6x plus 2 sine x. So adding in sine and cosine, all of our formulas work the same way. It's just another set of derivatives that we're going to have to get used to using. Let's try a couple more examples with sines and cosines. Example 10. Find the equation of the tangent line to f of x equals 3 cosine x at pi over 2. So again, to find the equation of the tangent line, we're going to need to find the functional value at pi over 2 so that we have a point, and the derivative at pi over 2, which will give us the slope. So f of pi over 2 means we're plugging pi over 2 into our function. So 3 cosine of pi over 2. So cosine of pi over 2 is going to be 0. So that means 3 times 0, which is also 0, which means that our point here that we're working with is pi over 2 comma 0. Now the derivative at pi over 2 means we need to find the first derivative of this function so that we could plug in pi over 2. The derivative of cosine we said was negative sine. So we have negative 3 sine of x is our first derivative here. Notice that I'm consistently pulling the negative to the front whenever I end up with a negative part of my derivative. So now I need to plug in a pi over 2. So negative 3 sine of pi over 2. So sine of pi over 2 is going to be 1. And so negative 3 times 1 is going to give me negative 3. And remember, that's the slope of my tangent line. So using y equals mx plus b, I have y equals negative 3x plus b. Now to solve for b, I'm going to plug in my point. I'm going to plug in a 0 for y and a pi over 2 for x. So here, I'm going to add this term over to the right, and that will tell me that b equals 3 pi over 2. Therefore, the equation of my line is y equals negative 3x plus 3 pi over 2. Now remember, this is the same thing as 3 halves times pi or 3 times pi over 2. So we can write this a lot of different ways that mean the same thing, but the convention is to combine the terms in the numerator to make it more simplified. Let's try one final example. Example 11. Consider the function f of x equals cosine x minus x cubed. Calculate the following quantities and round to 3 decimals. So here we're going to start with f of 2. That means we're taking 2 and we're plugging it into the original function. So here when we plug in 2, we're going to get cosine of 2 minus 2 cubed, which is 8. So cosine of 2 minus 8. If we were looking for an exact answer, that's how we would enter it. So if on your homework you're asked for an exact answer, enter it as cosine of 2 minus 8. However, in this problem, we want to round to 3 decimals. So we're going to plug this into our calculator, making sure it's in radians, and we're going to get negative 8.416. Next, we want to find the derivative at 2, which means that we first need to find the derivative function so that we can plug in a 2. The derivative of cosine, we said, was negative sine x minus, and the derivative of x cubed is 3x squared. So we want to plug a 2 into that function. So negative sine of 2 minus, if you plug in a 2 into 3x squared, you get 2 squared, which is 4, times 3 is 12. So again, if we were looking for an exact answer, we would enter it as negative sine of 2 minus 12. That's exact. It's not rounded in any way. But for this problem, we want to crunch that number to 3 decimals. So we're going to carefully enter that in our calculator, again in radian mode, and we're going to get negative 12.909. And then for part C, we're looking for the second derivative at 2. So first we need to compute the second derivative. So we go back to the first derivative and we take the derivative of that. The derivative of negative sine is going to give me negative cosine because there's a negative 1 in front that's multiplying, minus the derivative of 3x squared, which is going to be 6x. So now when we plug in a 2, we get negative cosine of 2 minus 12. So again, if we wanted an exact answer, it would be negative cosine of 2 minus 12. But since we want 3 decimals, we crunch that number and we get negative 11.584. So quickly, let's remember what these numbers are going to tell us. So here, this negative 8.416, that's going to tell us that the function is negative at x equals 2, which means it's below the x-axis. Because the derivative is negative, that tells us the function was decreasing at 2. because again, if your function's decreasing, your first derivative is negative. And then finally, because the second derivative is negative, we know that the function was concave down at 2. So we have a negative value that's decreasing and concave down is what's happening at x equals 2. And all of that information we get by looking at the various values of the function, the first derivative, and the second derivative.